Hello, everyone. For everybody in the room, I've met you over the last few days, but for people online, I'm Cameron Yates. I'm here at the Darwin Centre for Bushfires Research. I'm going to be talking about some work that we've been doing with the ISFMI since 2019, trying to get some of the science together to develop these carbon projects. A few people might have seen this slide this week. The problem, we have global emissions, fire emissions. The top slide is burnt area, and the bottom slide is the emissions. As you can see, through that equatorial belt, particularly in the savannas, there's a lot of emissions, and 62% of global emissions actually come from savannas. As you can see quite clearly in that slide, there is ample opportunity in Africa. There are big savanna emissions, and we are working towards getting some numbers to actually look at what those emissions might actually be on the ground. So if we step down and we look at Southern Africa, we have the fire scar mapping from Modus, the automated product. On your left-hand side, it's the total fire frequency. It's the entire archive from 2001 to 2021. You can see anything that is yellow, there's quite frequent fires, one in 3 years, and it's burning very frequently. And you can see that across Angola, Zambia, Mozambique, northern Botswana, and Zimbabwe, through the top half of Namibia as well. On the on the right-hand side, it's the frequency of late dry season fires. So at the moment, we don't have an ecological cutoff for what we will call late dry season. In Australia, we call the 1st of August the start of the late dry season, and all of our calculations are done looking at early dry season fires up until the 31st of July, and then it becomes late dry season. We don't quite know what it is in Africa at the moment. We haven't done that work to assess when the season changes, but for this example, we've just used the middle of the year. 1st of July is what we're calling, and we have been calling the start of the late dry season. So if you look at these two, you can see that there's not a large difference in the fire frequency between the total fire frequency, which is early and late late fire frequency, which means that fires are predominantly a late dry season problem in Africa. So why does it matter if it's an early or late dry season fire? Well, if we look at the effects of fire at different times of the year, again, on the top, we have in the early dry season, fires are very low, they're patchy, they don't scorch much of the trees, they don't burn all of the fuel on the ground, as opposed to the late dry season in wildfire scenarios where you are consuming a lot more of the fuel, you don't have patchy fires, they're complete burns on the ground, and so there's more emissions. And so this comes to some work which has been done by Guido's team. We used it in a recent publication as well. So this is actually emissions for Southern Africa, which Guido's team has put together. And for each country, the monthly emissions, the graphs are monthly emissions for each country. And you can quite clearly see that all of the emissions coming from every single country in this southern part of Africa are all late dry season fires again. There's very little emissions in the early dry season. So we're embarking on addressing this, as we've been talking all week, with a carbon methodology. And so we have been working towards getting data to actually put a methodology together. So we're restricting it to the Miombos in Southern Africa, and particularly just in the green part, the Miombo, and the Bikia forest as well. We're not including the other parts. So it's just the green and red parts that we're actually talking about developing this methodology for. I do have questions for people. So I'm trying to give information, but I want some back as well. Whether this is the most up-to-date Miombo mapping, this is the one we've been using. Hopefully people will let me know as we go through what the most appropriate, and I've got a few questions like this as we go through. So some examples of these. So am I able to move this bar at all, Andrew? No. So this is an example. We're talking about vast landscapes. This is a flight in Botswana, in northern Botswana. Very large, deciduous. This is a very large area in photo that we took in the late dry season in Chobe. You can see that all the trees in this example are deciduous. Very big landscapes with little access. Here's another example, slightly up. So that last example was in low rainfall. It was around 650 mils of rainfall. Moving up a rainfall gradient. This is some dry Miombo in Kafue National Park. In this example, the trees still have, some of the trees hold their leaves all year. There's also a decent shrub layer through these dry Miombos in Kafue and around the region. And then as you go further up the rainfall gradient to above 1,000 mils or above 15,000 mils, the canopy is getting closer. There's more trees, but it's still a savanna landscape, lots of shrubs. So as you go up the rainfall gradient, it's very similar to Australia, where the more rainfall you have, the more trees you have, the less rainfall, the more open it is. And then I'm not sure if this shows up particularly well here, but it's just some examples of some of the fires that we've been lighting there as well. So the top slide is in Chobe National Park. It's a patchy fire. The trees, it's an early dry season patchy fire. The trees aren't scorched at all. Not all the landscape's burnt, as opposed to the bottom one where you can see it's a late dry season. It's a bit further up, but all of the ground fuel has been consumed and it's not patchy at all. It doesn't really show up particularly well. So with developing the methodology, we've been, I was hoping sometime this week that somebody would put up a slide of what the rainfall and the environment is like in Australia, but it's extremely similar. This part of Africa is extremely similar to Australia. So if we're looking at rainfall and seasonality, it's almost the same. So from northern Botswana, you get around 600 mils. And as you go up to this one on the left is total rainfall. So northern Botswana is around 600 mils. And as you go up through Zambia, it gets to about 2 meters at the top of Zambia. The slide in the middle, it's hard to see, but it is the driest 6 months of the year. So all that yellow part of the landscape, the driest months are from May to October. The orange parts are April to September. And then the last slide all the way on the right shows the total percentage of rainfall that occurs in that driest 6 months. So these lighter colours, it's less than 5% of the rainfall occurs in the driest 6 months. So it is very similar to Australia in terms of it has a wet dry season where all of the rainfall falls over the Christmas months, and then you have a prolonged period of drought, which drives the savanna system and the fires. So you have a lot of rainfall, you have your fuel growth, everything's green. And as the year continues, it cures and cures more through the year. So in the later of the year, everything's completely dry and you get bigger fires. Pardon? Okay, sorry, I'll go a lot faster. So we've been working in Botswana and Zambia since 2019. We've done so much field work there over the last few years that we are now Botswanan citizens. This is an example of where we've been doing our research. We've got plots in northern Botswana. They move up a rainfall gradient into northern Zambia. I've delineated two colours here. It is rainfall. The green rainfall is below 1,000 mils. The blue rainfall is above 1,000 mils. The important thing to note from this slide is that the plots we have collected are from a rainfall gradient of around 650 mils to about 1,400 mils. We've collected a lot of data, both in woodland, open woodland, Zambia and Botswana, down that rainfall gradient. The slide on the top shows the amount of transects we've collected for fuel accumulation and then consumption as well. So what do we do when we're on the ground on a plot? We're measuring fuel accumulation. We run tapes out. We collect fine and coarse fuel. We actually do destructive sampling. Then we count shrubs in 4 different height classes. We measure heavy fuel. So we're going through all of the combustible layers, count the trees, the combustible layers. We collect data in each. We do dry sampling so we can get total wet weight. And then we do post-fire combustion. So we put plots in, we burn them while the fires are going. Our colleagues from the Netherlands have been flying drones and doing emissions, which Roland will speak about after. Tom's been doing patchiness flights. And then we run the tapes out after the fire and do the same measurements again. We measure how much fine fuel's there, how much coarse has been consumed and heavy has been consumed. And from that, we can start deriving fuel accumulation curves. What I've done here is on the left, I've got African fuel accumulation, on the right, Australia for a similar fuel type. And I've just put it up as an example to demonstrate that it is quite similar. So if we look at the fine fuel curve, it goes up in Africa to around 3.5 tonnes after 6 years, with time being on the x-axis and tonnes of fuel per hectare on the y-axis. In Africa, 3.5 tonnes after 6 years. In Australia, it's around 4.5 tonnes. The coarse is similar, the heavies are similar, but a very big difference between the Australian savannas and the African savannas is in the shrub layer. There's about 8 tonnes average that we've come across, as opposed to similar systems in Australia where we have only around 1 tonne. So it's a very shrub-dominated system. We do exactly the same with the post-fire. Early in the year, late in the year, get measurements. And again, comparing Australia to Africa, the consumption figures aren't quite as high. So in the patchiness, the fine fuels, they're not quite as high because the way that the structure is, there's more leaf litter rather than grass, and it doesn't get consumed in the same way. But the important thing is that there is more consumption in the late dry season than there is in the early dry season. But you can also see across each of the classes that they are similar. So I'll just run through an example for the Chobe project area, looking at emissions. So Robin was talking a bit earlier about this Chobe case study. So what we can do is if we have a quick vegetation map of open forest and woodland, we have the fuel accumulation curves and we have the consumption data. If we can then map fires, for any given year, we can use the time since fire, the seasonality of the fire and the vegetation to start to do calculations. I'll skip across this very quickly. These are just the calculations to come up with the emissions. An easier way of looking at it is the mass of fuel equals the area burnt, the fuel load, and the burning efficiencies multiplied by the emission factors. So for Chobe for this Chobe project area, I can then go back through time and calculate emissions for each year. And for the Chobe area, with 2022 only been up until October, for around a 6,800 kilometre squared area, there's almost 50,000 tonnes of emissions going up on average every year, which is quite significant. That's a lot of emissions. And so with a project, if they can reduce those emissions as they do in Australia, they can sell those. At the moment, all the work that we have been doing up this rainfall gradient has purely been looking at just the greenhouse emission side of things. We haven't looked at living tree biomass or non-living tree or the soil organics. People will talk to that. We just had one presentation talking about sequestration. I think we've got another one. It's also given us the opportunity to work with some wonderful people in the field. There's great people on the ground that are all enthusiastic, wonderful to work with. And because everyone's been so tired, I'd just like to say that it's not just in these chairs here that people fall asleep as well. It can be tiring out bush and people do fall asleep out there as well. Thank you. Is there one question?
One question.
Thanks. Just in terms of your estimations for the released greenhouse gas emissions, how did you estimate the ones from, from 2014 onwards? Is it based on satellite data of the vegetation cover that you had access to, or?
So what I did is I did all of the proper calculations for 2021, and then I divided the total emissions by the area burnt for both the early and late dry season. I should have put that up there. It is an important thing to say. In the early dry season, from these data, which is just from the low section, the lowest plots we have around northern Botswana, in the early dry season, about 9 tonnes per kilometre squared is burnt. 9 tonnes goes up per kilometre squared in the early dry season. I think it was 22 or 24 in the late dry season. And that's a very important thing for people to know, that there's probably 2 to 3 times the amount of emissions going up in the late dry season. So if you burn exactly the same area in the early dry season and completely replace it, you're still going to be making very good progress, because you're saving, 13 tonnes per kilometre squared. Yeah. Thank you.